So in the last video, we saw the Nullstellensatz, which told us about the correspondence between affine varieties and ideals, and said that if you take x and then take the ideal and then the vanishing locus, then you get back x. And if you start with an ideal and take the vanishing locus and then the ideal, then you get the radical of this ideal. And so this gives us in particular bijective and inclusion reversing correspondence between affine varieties in AN and radical ideals in this polynomial ring in n variables. And today we are going to see some consequences of this. And the first is that we have a very nice correspondence between points in AN and the maximal ideals in this ring. And you can get this correspondence by just starting with any point, and sending it to the ideal, which is generated by these linear functions x1 minus a1 up to xn minus an, which happens to be exactly the ideal of all functions vanishing at this point. And first, I wanted to just show this proof using a bit of a pedestrian technique, also recalling a bit about these maximal ideals. So to see that this map here is well defined, that this is indeed a maximal ideal, we can, for example, check that if you take the quotient here, then it is a field. And with a very particular field, it's just the ground field K. And you can get an isomorphism here by sending the equivalence class of a map F to its evaluation at the point A. And then if you have anything in this ideal and you evaluate at the point A, then you set xi to ai, and then all of these functions, of course, vanish. And so this is a well-defined map. And then you can check there's an isomorphism. And in particular, this quotient is a field, and so mi is maximal. So all of these things which we obtain like this are maximal ideals. And for the injectivity, you can check that you can reconstruct A just by taking now the vanishing locus. Because, I mean, the vanishing locus of the system of equations x1 minus a1 is 0 until xn minus an is 0 is exactly the point where xi equals ai, so exactly this point A. And since you can reconstruct A from this data here, the above is an injective map. And then finally, so this we could have done without any use of the Nullstellensatz. But then for the third activity, to say we have any maximal ideal in here, then the claim is that the vanishing locus here is non-empty. And you can kind of see this might be something which deserves to be called Nullstellensatz, and indeed that's one kind of alternative formulation, or at least consequence of the Nullstellensatz, that if you start with this maximal ideal, then there is a solution. And to see that, well, we can do the proof by contradiction. We can assume that if this was empty, then we would, of course, have the ideal of this vanishing locus is the ideal of the empty set. But which functions vanish on the empty set? Well, everything vanishes on the empty set, so we get the entire ring. But this is, of course, not the square root of m, which would be predicted by the Nullstellensatz. And since m is a prime ideal, its radical is actually just the same thing as m itself. And so we get this contradiction, and so this must have been false. So v of m is indeed non-empty, so we can pick any element here. And then this element, I mean, this gives you an inclusion of this set into this vanishing set. And then taking the ideal on both sides gives you that the ideal of A, which is just MA, contains, so the inclusion reverses, contains the given maximal ideal. But since it's maximal, we actually have an equality. And so indeed we could obtain this given maximal ideal from this form MA. Okay. So this was the kind of pedestrian way of proving it, basically going back to commutative algebra facts. There is a nice alternative proof, which takes kind of a very high level point of view and uses this correspondence which we had before. So here the corollary says the points correspond to the maximal ideals, and you can just get this as a consequence of this general inclusion, reverse, and bijection between affine varieties and radical ideals. Because on this side here, the sets with a single element are the minimal non-empty affine varieties, which means whenever you give me any affine variety, of course, I can just take a point in there, and then the point is the smaller, possibly smaller affine variety. And so these are minimal with respect to inclusion, such that you're still non-empty. This is on this side, and then the inclusion reversing correspondence says that, well, their ideals on this side must be the maximal and proper radical ideals. And then you just need to see that an ideal which is maximal among radical ideals is also maximal among all ideals. And well, I mean, if you had an ideal which is maximal among radical ideals, and then there is another bigger ideal in there, then this bigger ideal is itself contained an even bigger maximal ideal, and but that maximal ideal is again radical, and then so the original ideal that you started with is then contained in a bigger radical ideal, and that gives a contradiction. So, I mean, this last part, you should kind of convince yourself that this maximal among radical ideals is the same thing as being maximal among all ideals, which are proper. Okay, but so somehow we can see this result in two different ways. So this was one consequence, and then another is that we can now upgrade some of our properties of this ideal of vanishing things. Namely, if you give any affine varieties x1 and x2 in AN, then we can say what the ideal both of their union and of their intersection is. So the ideal of the union is the intersection of the two ideals. And the ideal of the intersection is a bit more complicated, namely you take the sum of the two ideals, but then you need to take the radical afterwards. And the proof is left as an exercise, but I think it's a good exercise because you can then see where does the Nullstellensatz appear here, and also recall a bit about these about the ideal of functions. There is a fun exercise, I would say, because you see in this lemma we had as input that x1 and x2 are affine varieties, and in all of the previous results we basically just allowed any input, like any sets, any subsets. And it just turns out that that the statement in B is false if you allow any subsets. And you can find, you can try to find a counterexample by just taking n equals to 1, and for simplicity you can work over the ground field k equals to the complex numbers. So you can try to see if you can find examples of subsets such that this statement here is false. And the fact that this is possible tells you that, at least for this part B, it's important to allow x1 and x, or to use that x1 and x2 are indeed affine varieties. So it also gives you a bit of a hint how you can approach this exercise before. Okay. And to see that this square root is really necessary, we can look at a short example here. So we can inside A2, take two affine varieties, namely x1 is the vanishing locus of x2 minus x1 squared. And so this is basically, so if x2 is y, x1 is x, then this is y minus x squared. So this is basically the parabola, y equals x squared. This. And the second affine variety is just the vanishing locus of x2, so basically where y is equal to 0, like this. And so if you intersect them, then, well, I mean, geometrically, you see you get just the origin, like this. And on the ideal side, we can now compute like what is the ideal here and what is the ideal here. So if you take the sum of these two ideals, so you just take the union of the generators here, and then you can see that you can replace this generator by subtracting the other generator. That's always that always leaves the ideal constant, and you can get rid of the minus sign here, and then you get a very simple form. It's just x1 squared and x2, and then what the lemma tells you is that the ideal of the intersection should be the radical ideal associated to this. And then when you look at what a radical here is, what you see is that, for example, the function x1 has the property that some power of it is contained in here, namely x1 squared, but x1 itself is not contained in here. And so the ideal after taking this radical really does get bigger. And then the ideal that we do obtain, the x1 comma x2, is of course exactly the ideal of the origin, which is the unique solution of this system of two equations. And so you see that just taking the sum, you get an ideal, and the vanishing locus of this ideal is still just the origin, but it is not the ideal of its vanishing locus, and to get that, you need to take the radical. So these are really different. And so everything works, the lemma is fine. We do see here that that we lose a bit of information in a certain sense, because I mean this parabola and this line, they meet at this point, but they meet to order 2. I mean, we haven't really defined what this means, but like intuitively, you could, for example, say if you parameterize this line here, and then you plug this equation here into this parameterization, then you get the polynomial x squared here, so which vanishes to order 2 here. Or you could see that somehow the two curves which you get here, they share a tangent at this point. So there's different ways to see that these meet with some higher multiplicity at this point. But then after we just take their intersection, their set theoretic intersection as affine varieties, and take the ideal, this information is lost. We just get the standard point. And later, we will generalize from the setting of affine varieties to the setting of affine schemes. So we will introduce this notion later. And then we see that the scheme theoretic intersection of these corresponds in some way to the actual ideal x1 squared and x2. And you see in that ideal, we remember there's a multiplicity 2 in the intersection. So we will be able to have more information available to us. Okay. So this was the example dealing with ideals of unions and intersections. And then finally, there is a nice corollary of the Nullstellensatz, which just says that if you have any ideal, then the following are equivalent. So its vanishing set is empty, and the ideal is actually not a proper ideal, but it is the whole ring. And see that 1 or any unit is contained in the ideal. And so in other words, if you are given a finite list of polynomials, which would be the generators of this ideal, then one of two possibilities must occur. Either there exists a solution of this common set of equations, and then that solution you could call the Nullstelle of so the zero set or the zero locus of this system of equations. Or on the other hand, maybe 1 is in the ideal, and so it means that you can find some coefficients g1 up to gr, such that this linear combination of these points is exactly 1. Okay, and so this is a maybe more intuitive version of the Nullstellensatz, which just says that if you are given a non-trivial set of equations, then it has a solution. And in fact, it's not extremely hard to just take this Nullstellensatz as an input and then recover the full version. And I mean, just to see like how do you obtain the Nullstellensatz? I mean, the fact that an ideal is equal to the full ring if and only if 1 is contained in there, this is pretty standard. The fact that B implies A is just, I mean, the vanishing locus of the entire thing in particular is contained in the vanishing locus of 1. 1 vanishes nowhere, and so this is empty. And the other direction, that if the vanishing locus was empty, then your J was already the entire thing. This follows very similar to the proof that we had, because then well, we already saw this right here. So if we assume the vanishing locus of an ideal is empty, then we get a contradiction, because then the ideal of this vanishing locus is everything, but it should also be the radical of the original ideal. And so in particular, we see that everything is the radical of this ideal. So it means that for the element 1 in here, some power of it must be contained in the original ideal. But any power of 1 is still 1. And so 1 is contained in the original ideal. And so in this way, we can prove that A implies C actually. And then we have the full equivalence here. So this was one reformulation of the Nullstellensatz, and that also finishes this video.